Thank you, and welcome everyone to this half an hour introduction into the tools that we at KDAB have developed and actually decided to release out in the open as open source. So everything that we'll be talking about here you will find on GitHub, I think, or KDE sources. Everything is free of charge. Please use it and maybe even contribute back. So maybe before I actually start showing you the individual tools, some background on why we actually do that. Because you may wonder, well, that looks pretty cool. Why do you release it free of charge? Well, we don't earn our money by selling these tools. We earn our money by solving hard problems with these tools. And it turns out that most of these tools fill a gap, and we've seen again and again that Qt developers run into the same issues or the same problems. And using these tools actually enables all of the Qt developers to become more efficient developers, to write better code. And turns out the problems that remain are still the hard ones, so we are not losing any work, right? It's just the simple stuff that is gone. So let's dive right in. What we are going to talk about is 4 tools. Clazy, static code analysis tool specifically meant for Qt, but also now some special checks generic for C++. Gamma Ray for a high-level debugger tool and introspection tool to Qt applications at runtime. And then the third one is HeapTrack, a memory profiler on Linux that I created, and Hotspot is another tool that I have spearheaded, which is a UI frontend on top of the Linux perf subsystem, so sampling profiler, and we have created a nice UI around that, which makes it easier to use. So, static code analysis tools. There are, I believe, millions of them out there, and most of the good ones actually cost tons and tons of money. But it turns out that thanks to Clang, this this compiler and the compiler framework that has been released out in the open, it's actually pretty easy nowadays to write your own static code analysis tool. And a colleague of mine, Sergio, took this idea and implemented checks specifically for the pain points he has seen again and again in code reviews, and especially code reviews of C++ code using Qt. So here's one example. Can you spot the issue? Very common. You have an if-ndef of some macro, and then you define that macro, but there's a small typo. You probably didn't mean that. There's a missing G in the first if-ndef, and Clazy will spot that and tell you maybe this is not what you intended. So Clazy is a plugin you can inject into Clang while compiling. So if you're using Clang for compiling, you can just enable the plugin at runtime or at compile time, and you will get more warnings, which is pretty nice. What else is there? You have a polymorphic type. It has something virtual in it, but that class is copyable because, well, you didn't define anything, no copy operations, no constructors, so the compiler will auto-generate them for you. So you now could copy this class, but probably you didn't want to because it's virtual, so that has the potential issue of introducing slicing. So this is another very common coding error where you could end up copying a subclass of this base, and then you would lose the information or the type information. This is called slicing. Probably an error. But again, it's static code analysis. This is probabilist stuff. You don't really know whether it's a hard error. There are many more like that. But the cool stuff, in my opinion, really still is the Qt specifics, because they tend to be hard errors that whenever we see them, we can be pretty sure, no, this is wrong. This is one of these examples. We have a value on the stack, our variable a, and we have some lambda f, which is actually not used in the, so ignore the f, I forgot to remove that. the important part is the last two connect statements using the new pointer to member connect syntax. Both take a lambda. One takes A by value and one takes A by reference. The compiler will compile this just fine. It's not an issue at all, right? But from a conceptual semantic point of view, we will know that the second line is always wrong. Because semantically speaking, you're connecting a lambda that takes a reference to something on a stack. And whenever the lambda will be executed, so semantically speaking, when the signal is emitted, you will be outside of the scope of this function test. So the reference of A will be dangling. And it will crash, actually. And we've seen this crash a lot of times. I've written code like that. I've run into this crash. But nowadays, we get, thanks to Clazy, that warning that you're capturing a local variable by reference in a lambda inside the connect. So this is very specific. You just get this one issue here, which is also showing that actually line 4 with the auto f equals some other lambda, it has some meaning because we don't get a warning there because we're not passing that lambda to a connect statement. So we won't get drowned in warnings wherever we do that. Only when we use this inline lambda, because that's where you usually get these errors. And there are more checks like that specifically meant for Qt code. Another one that I personally care about a lot are situations where you write code with Qt, and the code is really nicely readable, you like it a lot, but turns out you just introduced a paper cut. And the more you add, the more likely you are to die of a death by 1,000 cuts. Meaning, the code you've written here is nice, it's readable, but it's actually quite slow. Do you know why? Turns out both of these can trigger memory allocations whenever you execute them. The first one, I think, got fixed in newer versions of Qt, but older ones actually executed a memory allocation whenever you did the comparison, because it converted the foo string literal to a Q string every time you did the comparison. Because Q string is UTF-16 internally, the foo literal is UTF-8, and that is slow. It's a memory allocation. The second one will be allocating even in the latest and greatest of Qt, because you have a QLatin1 string as a return value, but the type returned is a Q string, so there will be a silent implicit conversion happening, which is allocating memory. And now you can imagine you have code like that all over your place. Well, Clazy will find all of them automatically for you. And not only that, it actually comes with fixits for some of these problems. So now you can, if you run Clazy manually or as a Clang plugin, define this environment variable, rerun it, and it will go through your code and change it for you. In the first case, it wraps the foo literal in a QLatin1 construct to ensure it's not allocating memory whenever it does that. And in the second case, it's not using QLatin1 string, it's using QString literal, which constructs a QString at compile time in UTF-16, and then you can just hand it out all the time. So now, suddenly, the static code analyzer becomes the tool to just rewrite our code for these common issues we've seen again and again. And recent versions of Qt Creator actually embed Clazy. So you can go into Qt Creator, configure it such that while typing, you'll see the Clazy warnings inside your editor. If you want to see that, come to our booth. I don't have it set up on this machine, but at our booth we have it all set up, and you can see it happening live while writing the code, which is awesome, I believe. So this is Clazy. And I really like it. It's something where you really don't have any reason not to use it, especially now that it's integrated in Qt Creator, or if you use Clang, or even if you're not using Clang, just get another CI machine up and running with Clang, with Clazy enabled, and then get your nightly builds checked with Clazy warnings enabled. So that's static code analysis tool. Now, the second tool we're going to talk about is Gamma Ray. It's been around for a long time now, but it's still super valuable. And what makes me kind of sad is that that despite its age, every year at World Summit or Dev Days, I meet new people, new developers that are quite familiar with Qt for ages, who haven't heard of Gamma Ray and who are not using it. I don't get it. So again, this year I will show you a short live demo of Gamma Ray and why I believe it's an invaluable tool. And it's free of charge. There's no reason not to use it. You may know this same game example. It's a ship with Qt, Qt Quick. It's a demo, little game, you can play it. Well, that's nice, but actually, how is this working at runtime? How is the QML scene built up? What issues are there maybe? What can I figure out about it? Maybe, what about the padding of the high score? Maybe I want to change the placement slightly, right? Usually what you would end up doing is edit the code, change the margins or paddings, rerun, and then see, did the change of 1 pixel more to the left or right, was it worth it? Yes, no, oh shit, it should have been 2 pixels. An alternative to that is simply using Gamma Ray. So you prepend same game with Gamma Ray, or your runtime attached if you like to. You still get your same game window, but now you also get this huge and large Gamma Ray window in the background. And one important aspect here is that these are actually 2 separate processes. You have your same game debuggy. It could run on a different machine. It could run on a completely different network. I don't care. You just inject Gamma Ray there, and then on your development machine, maybe running a completely different architecture. So maybe that's embedded ARM, and I'm Intel x86 or so. I'm running this large view. And now here I can dive deep in. By default, I see the QObject parent-child hierarchy. This is a QGUI application. I probably have a window somewhere. Or not, because it's QML. But somewhere I'll get something. I have all the properties, methods, connections, stack traces to where this function was, or this object was actually created. And even nicer, I can go to this so-called quick scenes tool on the left-hand side. And now here I see running live the game, which again, this could run in reality on a completely different machine. Yeah? I use this when I work from home and I need to work on a customer project that is running on some embedded hardware in our office, right? Set up VPN, connect to Gamma Ray, and then I have same game running on the embedded device and Gamma Ray on my local host. And why is this cool? Well, turns out I can, let's disable that. I don't want to show you that yet. I can redirect input and I can interact with the application remotely, for example. Well, okay. But what else I can do is I can actually pick elements. So for example, this text element, and whenever I pick something, it gets highlighted in both the view here as well as the tree on top. I see visualized the paddings, the margins, their values, and I can go in and then say, well, I want to change the padding. Oh, that's not what I wanted to do. So I can change padding values, or better yet, let's change the text. This is my current score, by the way, so I'm cheating. And as you can see here on the right-hand side, I now suddenly have a score of 8 million or so. Well, the point is, of course, not to cheat, but to change properties at runtime to see how they influence the behavior of your application. And this can often make you much more efficient as a programmer because you don't need to go into this copy-edit cycle and recompile and redeploy cycle, right? And even better yet, we can at runtime trigger some of the fancy visualizations built into Qt Quick, like visualizing batches. And I edited the same game example here to enable clipping on all of these blocks. And when I visualize batches, the visuals change completely, but now I'm looking for areas like this one. When it's one color, I can know this is one draw call or draw operation. But here, all of this is colorful. Their batching is broken, is probably bad for performance. And usually without Gamma Ray, you have to enable this visualization before you start your application, and then it will look like that all the time. And now you have to say, okay, I wanted to go to this one dialog, which is like 5 levels deep. How do you do that, right? With Gamma Ray, you can just toggle it as you go to the dialog you want to, and then enable the visualization or disable it again, which is very helpful. There's also one that shows clipping. So it may be a bit hard to see in this case, but there's now this red area here, which is elements that have clipping set. And that clipping is what destroys the batching, actually, in this case, the way I edited this game. I can also visualize overdraw. So this is now our view box. And oftentimes what we see in customer code is that people write QML code which paints all over the world outside the view box. Because for some animations, you actually need that. But then afterwards, once the animation is done, you should hide the stuff that is outside the view, because otherwise you're just wasting resources for nothing, because the user won't ever see that, right? We see that again and again and again. With this, you could see it visually. And you can also go to the problems tool view, which is relatively new, start to scan for problems. And now it will look at the current state and finds issues such as, very common, visible items that are outside of the view, just what I talked about. But now you can go in and say, where is this smoke text? I can go to the QRC file that created this. If it's not using QRC, you would be able to jump directly to the source code on file, because, well, we also know all of the resources that are inside your application, right? And now I can see this is the QML file inside the QResource file that created this object that is outside of the view but still visible. You probably want to hide it. And there are more and more tools like that. We have a similar view for widgets, Q3D, you name it, state machines. So let me show you a screenshot for the state machines here. I really like that as well, because when you're debugging state machines, it's pretty hard actually if all you have is log. Because the log file, well, you need to add all of the information that you need. But once you visualize a state machine, and Gamma Ray will do this for you, for every Q state machine, you will instantly see whether there is a bug inside your state machine, because that's the model of a state machine. It makes it very easy to spot issues graphically. If you have a state that is not connected at all or wrongly connected, it will punch you in the face when you look at it in Gamma Ray, and it's like, oh, that's the issue. Now I get it. And if it would actually run, the blue highlight would follow the current state that is active, and you can get a really nice insight into your state machines. So think of Gamma Ray as a debugger at runtime on a very high level, specifically meant for Qt, right? It's not stepping along instructions like GDB. It's like having the visuals and looking at them. If you have the Qt Automotive Suite, you even get that into Qt Creator, nicely embedded. But even without that, you can just download Gamma Ray and run it outside of Qt Creator free of charge. Which brings me to tool number 3, Heap Track. Heap Track is a memory profiler. So far, Clazy was static code analysis tool to check for common issues. Gamma Ray was a debugger for high-level issues. And Heap Track is now profiling for memory consumption, because lots of our customers have asked us to look into memory consumption on memory-constrained embedded devices, for example. And before I started this project, I wasn't aware of anything except Massive on Linux at least. But Massive from the Valgrind suite was actually pretty damn slow, and it wasn't often feasible to run it on an embedded device. HeapTrack is pretty fast compared to Massive, definitely, and it tracks each and every allocation your application is doing and records all of that into a data file, which you can then, after the fact, analyze. And the cool thing is that, contrary to Massive, I don't throw away any of that information, meaning we don't only get to see how our memory consumption is evolving, I also see the number of allocations we are doing, and we can find so-called temporary allocations that are often quite easy to remove and thereby enable us to run our code faster. Let's show this in action. So this is code I've written for this training we've been running yesterday, or there's another one coming up next week for 3 days in our offices. And it's written explicitly in a bad way, such that it shows you how you could use HeapTrack. So if you just run it, so usually you would run your application. Now you either, again, runtime attach or record from the start. You prepend HeapTrack, you run your application, and it's not that much slower than before, right? I mean, it's not like Massive, which would have taken 10 times as long, or even sometimes 100 times longer, right? It's, let's say, twice as slow sometimes. It depends on your workload, really. And now we got this HeapTrack data file. It's compressed, and I can open it and analyze it. And we are greeted by this overview, which shows us already how many allocations are we doing. Well, this is 3 million allocations, which is quite a lot, I believe. The peak heap is close to 600 megs. And even worse, when we look at the total memory leaked, most of our peak gets leaked. So already here we see, something is wrong. In the summary page, we also see the largest memory leak, and already here we see a function that we have written, and where it comes from and how much it allocated, how much the peak contribution was, and this seems to be a real issue. You can also look at it graphically. This is the memory consumption over time, and it's actually quite fine-grained. Roughly every 10 milliseconds we get a data point. And we see, well, yeah, there's definitely something wrong, right? This is not how it should look like, usually. Depends on what you're working on. We can then go into the flame graph visualization, look for the leaked one, and indeed it's just this one function that really takes all of the leaks home. But we could also look at memory allocations. There the picture is a bit more complicated. We have different locations that have triggering allocations. And this flame graph is really a visualization of the bottom-up and top-down views. So you can change in the flame graph whether you want to see the bottom-down or the top-down view. And now, if we actually want to look at this starts with location, I just search in the function. In the caller callee view, I see starts with in mail parser line 26. Well, let's open that file. Oh, and I haven't set it up correctly. Sorry for that. So what was it? Mail parser line 26. And well, we get to this line, and indeed, this is very, very bad code that I've written. I kind of like it because it's so bad on so multiple levels. The point here really is it's pretty easy to find these issues with HeapTrack. And contrary to other leak checkers, we actually see them over time, right? Which is kind of nice. And we could also now go in and find temporary allocations, like in an example like this one here. Remember with Clazy would also once again warn you there's a memory allocation happening here whenever you run this, because this QString literal will allocate. Instead you have to write QString literal and then the actual literal. or a QLet in one string, right? Clazy would find it at compile time. HeapTrack will find this at runtime and show you tons of temporary allocations, and oftentimes it's very easy to fix these performance issues then. So that's HeapTrack, and now I have 5 minutes left for Hotspot, which is a UI on top of Linux Perf. And those of you who haven't used Linux Perf yet, it's good. You probably should start with Hotspot first, because then a lot of your pain you will be spared a lot of pain. Perf is awesome. It's super powerful. It's a Linux tool on the command line. But if you want to leverage it to its full extent, then you would have to know that when you want to profile an application, you would have to say perf record -- call graph dwarf, because unwinding needs to happen, and then probably you want to have switch events as well, and you want to look at cycles, and probably because you want to do off-CPU profiling, you also want to have, what is it again, scat switches. And I believe I have, per CPU, or what was it? Oh, well, I forgot it again. That's the kind of pain you had to go through earlier. With Hotspot, let's remove all traces here. All you need to do is say, this is what I want to profile, some parameters. I want to look at cycles, I want to have off-CPU profiling, and I want to have per CPU events. That's the standard defaults. Maybe this checkbox is all you need to tick, actually. Then you say, yep, start recording for me. And wait while your code is running. And this is supposed to be a concurrent threaded application. Let's see whether it actually is leveraging our threads. And we visualize the data now. And we get this nice summary view. And most importantly, here is that part over there where it says our runtime is 9 seconds. But on CPU, we were also 9 seconds, and off CPU, sleeping, we were for 5 minutes. It's not an issue, not an error on my side. It's really, we have been running for 9 seconds, and during 9 seconds, we have slept for 5 minutes. How can that be? What the hell? Well, let's look at the flame graph, and most importantly, this timeline view at the bottom here, where we see, oh, there are a lot of threads here. That's not a good idea. And even worse, on top, we see these per CPU costs. The orange bars mean something is running on CPU. Well, this is not running in parallel, right? It's only running on one CPU pretty much all the time. I could now go in and say, what is going on here? Right-click. I'm just interested in this CPU and actually only in that section here and only for this thread here, please. And while doing that, the view on top will update itself all the time, which is pretty nice. And now I can look at cycles, which is on CPU time, so I can use that to fix performance issues where I'm actually running. Or better yet, I can look at scat switches. That's just the number of context switches, probably not too interesting. Context switch means the kernel figures out that we have asked not to work. For example, nanosleep or Mutex Lock contention or something like that. The kernel switches us out and some other process can run. But the number is not that important. The time difference is important. That's where this off-CPU time comes in. And turns out, well, you go from bottom to top in this flame graph until you find code that you've written yourself. This first pass Mandelbrot row, I wrote that. Let's view caller callee. Lots and lots of data. The important aspect here is when I look at the right-hand side here, these are the locations inside the function that I just selected on top. And I can sort by off-CPU time and see apparently Mandelbrot.cpp line 124 is to blame. Let's open that one. And oh wonder, it's a lock, a Mutex lock. In this first pass Mandelbrot, you would have to study the code, is something you pass to the queue thread, and the first thing it does is it locks the thread, the mutex, and this, of course, stars the other threads, and you're suffering really, really badly from lock contention. But you can nicely find that with Hotspot nowadays, which is pretty awesome, I think. So I think I'm running out of time. Yes. Thanks for listening. If you have questions, come to our booth. I can show it to you in more detail if you want to. Thanks.